Hi everyone, this is our video on bending stress in elastic plastic materials. So first off, a quick intro on bending and bending stress. So bending stress is the stress that a member, such as a beam, experiences due to bending moments generated from different types of loading. Bending can occur in three main ways. The first way is through what's called pure bending. Pure bending happens when equal and opposite moments, which act in the same plane, are applied to a beam. An example of pure bending is a barbell. As a weightlifter lifts the barbell up, bending moments are generated at either end due to the weight, and these moments cause the barbell to bend slightly, which in turn produces bending stress. The second way bending can occur is through transverse loading. So when a beam experiences transverse loading, an internal shear force and bending moment are generated throughout the beam, and this bending moment in turn produces the bending stress. An example of transverse loading is a fixed horizontal cantilever beam. By applying a vertical or transverse force to the free end of the beam, an internal shear force and bending moment are generated. And then the third way bending can occur is through what's called eccentric axial loading. Now, eccentric axial loading is a type of axial loading that does not actually pass through the centroid of the object, and it's the off-axis nature of the loading which produces an internal axial force and bending moment. An example of eccentric axial loading is a clamp. As a clamp is closed down, axial forces push upwards on the clamp's jaws, which in turn generates a bending moment throughout the straight section of the clamp. Bending can also occur symmetrically and unsymmetrically. Symmetric bending occurs when the bending load is applied along the axis of symmetry, whereas unsymmetric bending occurs when the bending load is applied away from the axis of symmetry.
Now, it's also important to note that in all cases of bending, there's a region along the cross-section of the member which experiences zero stress and strain due to bending. This region is called the neutral axis, and it passes through the centroid of the object. On either side of the neutral axis, the member will experience either compressive or tensile stress, depending on the direction of the bending moment.
Bending stress is very important to consider in both mechanical and structural designs. For example, when designing buildings, it's crucial to analyze the bending stress of load-bearing beams to make sure that they won't fail under the weight of buildings. Similarly, traffic moving across bridges will generate bending stresses due to the weight of cars, and so structural members need to be designed such that they can withstand the bending stress to prevent the bridge from collapsing.
Okay, so now I will get into the preliminary background. An elastic plastic or elastoplastic material is a material that has the properties of both an elastic and plastic material. This means that the material has a stress-strain diagram that is similar to the figure taken from the Chapter 1 lecture notes. This diagram shows that if the strain disappears when the stress is removed, the material behaves elastically. And when the strain does not return to zero after the stress is removed, the material behaves plastically. The elastic region of the diagram is where the material behaves elastically and is the region where the material can return to its original shape once the force is removed. The plastic region of the diagram is where the material behaves plastically and is the region where the material will face permanent deformation from the force and will not return to its original shape. The topic of this project is to study the bending stress in elastic plastic materials with perfectly plastic behavior. One of the most important things to understand then is what does perfectly plastic actually mean. On this slide, the stress-strain diagram for an idealized elastoplastic material can be seen. From this diagram, it can be seen that as long as the stress sigma, which is represented by the y-axis, is less than the yield strength sigma y, the material behaves elastically. When sigma reaches the sigma y value, the material starts yielding and keeps deforming plastically under a constant load. This is what it means for a material to have perfectly plastic behavior. It is when the material continues to deform without an increase in stress. The moment of a force about any point is defined as the force times the perpendicular distance from the line of action of a force to the point. This can be seen in the figure on the slide where the moment is taken at point A and is equal to the force multiplied by the perpendicular distance from point A to the force. The equation for the moment is shown as m equal to F times d. Stress is the intensity of the internal force at a point and is found by taking the ratio of force over the area. The stress at any point is defined by sigma equal to the limit as delta A approaches 0 of delta F over delta A, where delta F is the force on a small area delta A. The component of stress perpendicular to the cross-section is called the normal stress and is represented by sigma. The equation for the normal stress of any cross-sectional area can be defined as the equation on the screen, where sigma zz is equal to the limit as delta A approaches 0 of delta Fz over delta A. The first index z in this case shows the direction of the normal vector to the cross-sectional area, and the second index z in this case as well shows the direction of the force/stress component. The bending stress can be determined by first looking at a linear elastic and homogeneous material where sigma x is equal to the elastic modulus times the strain. This is then equal to negative E times y divided by rho. This is because the strain epsilon x is equal to negative y over rho. Then, for static equilibrium about the z direction, you can take the moment, which is equal to the integral of negative y times sigma x dA. This results in rho equal to E times I all divided by m. Substituting rho back into the original equation for stress gives us that the bending stress sigma x is equal to negative my over I, where m is the applied bending moment and I is the area moment of inertia of the cross-section. The bending moment m, corresponding to the nonlinear stress distribution in a member under pure bending as seen on the slide, can be determined using these two related equations on the slide. Equation 1 is determined by considering a member with a rectangular cross-section of width b, so this then means that the element of area is expressed as dA equal to b dy. This means the bending moment m is equal to negative b times the integral from negative c to c of y times sigma x dy, where sigma x is the function of y plotted in the figure shown. Since sigma x is an odd function of y, the equation can be rewritten as m equal to negative 2b multiplied by the integral of 0 to c of y times sigma x dy. This equation can now be used to determine the bending moment m for a nonlinear stress distribution in a member under pure bending.
Okay, so now that we've gone over some of the background topics, we're going to start introducing the concepts and the actual theory behind bending in plastic members. So from our materials course, we know that the yield stress is actually the point in which, or it's sort of like the boundary between elastic and plastic deformation. So I'm going to assume that we have a rectangular cross-section, and the max stress in this cross-section is equal to the yield stress of the material, just like we have on the right-hand side. So naturally, we're wondering what moment does this occur at? What moment do we have the max stress is equal to the yield stress of the material? So we're going to take our base stress equation due to bending, and we're going to rearrange for the moment. And we're going to actually find that this moment is equal to the area of inertia divided by c, which is just the max distance, times really any stress, but in this case, we're focusing on the yield stress. And we have that this moment, this corresponding moment is actually called the maximum elastic moment of a material. And this is the max moment that can be applied to a beam that still maintains elastic behavior. So there's no plastic behavior yet. So naturally, you're going to wonder what happens when we increase this, and this is what we're going to explore next. So you might be wondering, what happens when we increase the moment past this elastic point? And we're actually going to start to develop plastic regions in the material. So these plastic regions are going to start at a point furthest from the neutral axis. And as we increase the moment more and more, these plastic regions are going to grow. And now you might be wondering, how come the stress in these plastic regions is constant? Well, that's actually because of the concept of perfectly plastic materials. So if you think back to the stress and strain diagram of a perfectly plastic material, we have the linear region that grows, and then eventually once you hit the yield stress, the stress flatlines. So even though the stress isn't increasing and the stress is staying constant, the material is still exhibiting strain. So that's exactly what's happening here. We have these linear elastic regions that match up with the linear elastic region in the stress and strain curve, but we also have these plastic regions that have a constant stress, just like the perfectly plastic regions in the stress and strain curve. Okay, so now I'm going to solve for some formulas. So if you look at the elastic region of this material on the right-hand side, we can actually find a linear equation relating the normal stress to y, which is just the distance from the neutral axis. So we can actually get a linear equation for the normal stress in this elastic region. And next I'm going to move on to sort of the integral for nonlinear stress. So you should have seen this in our preliminary and background information section. So if you're still confused about that, I recommend you go back and rewatch that. But this is just an integral that relates the moment to nonlinear stress in a cross section. And then next, if you remember the max elastic moment for a rectangular cross section, we had that it's equal to the area of inertia over c times the yield stress. So we can actually simplify this or expand this by finding a value for I over c, which is just very simply using the moment of inertia equations for a rectangle and rearranging. And we get this formula right here. Okay, and now we can go back to that nonlinear stress integral we had on the previous slide. We can actually plug in some of our values. So the initial integral was from 0 to c times y times the normal stress. And we can actually break this up into the two regions. So we can break it up from 0 to yy, which is the elastic region, and then from yy to c, which is the plastic region. And then we can sub in our known values for the normal stress at this location. So from 0 to yy, it's going to be our elastic formula, and from yy to c, it's going to be the plastic, which is just the yield stress. And then we get the moment is actually equal to these two terms multiplied together. And if you look at the first term, it looks very familiar. And if you recall from the last slide, we actually had a formula for the max elastic moment in a rectangular cross section. So we can rearrange this formula and plug it back in, and we get that the moment is equal to 3 over 2 times the max elastic moment times 1 minus 1 over 3 yy squared over c squared. So now we actually have a formula that relates the applied moment to the max elastic moment to the size of the elastic region, or yy. So now we can use this formula to analyze a cross-section that's exhibiting purely plastic behavior. So we can take our formula and we can plug in a yy value of 0, and we actually get a value that MP is equal to 3 over 2 times my, which is the max elastic moment. And we can conclude that this is the bending moment corresponding to a fully plastic cross-section. And we could take it one step further and generalize it to any cross-section. We could say that this fully plastic bending moment is equal to K times the max elastic moment, where K is called the shape factor of that cross-section. So doing an integral for every single cross-section is going to get very painful very quickly. So we're going to introduce a new type of approach, which is more of a graphical approach. So consider we have two types of cross-sections. On the left-hand side, we have a max elastic cross-section where the max stress is equal to the yield stress. And on the right-hand side, we have a fully plastic region. And in each of these regions, we have a stress distribution. So if you think back to MTE 119 or statics, you'd know that the force in each of these stress distributions is equal to the volume. So in the max elastic case, we know the force is equal to 1 over 2 times the base times half of the height times the yield stress, which is just the volume of the triangular prism. And on the right-hand side, we have the force is equal to the base times half the height times the yield stress. And in each of these cases, we have two equal and opposite forces. So we can actually find the couple moment created by both of these forces. So to get the couple moment, we can take the forces and multiply them by the distance between the two. And for the case of the max elastic, we get 2 over 3 times bc squared times yield stress. And for the case of the fully plastic bending, we get bc squared times yield stress. And these are the exact same equations before, so we can plug them into our shape factor equation, and we get that our shape factor equals 3 over 2, which is saying, just like before, that the shape factor for a rectangular cross-section is equal to 3 over 2. So now we know that for any general cross-section, we can use the graphical approach to get the shape factor, and then from there we could just use the basic stress equations to get the max elastic moment, and now we have a way to solve for the max bending moment.
The next section of this lecture is the example problem. A member with a uniform rectangular cross-section experiences a bending moment m. Assuming that the member is made of an elastoplastic material with a yield strength of 250 MPa, determine A, if there is any elastic section of the cross-section, if so, how thick, B, what the maximum moment my is that results in the whole cross-section being elastic, and C, what the moment mp is that results in the whole cross-section being plastic. For this question, the dimensions of the cross-section is given, the moment is given, which is 35 kilonewton meters, and the yield strength is given. In order to figure out if any elastic section exists, we want to solve for the thickness of the cross-section. When I refer to the thickness of the cross-section, I mean half the thickness of the cross-section, which is yy. And when I refer to the height of the cross-section, I mean c, which is half the height of the cross-section. If we solve for the thickness and we see that it is 0, this means that there is no elastic section in the cross-section. If the thickness is in between 0 and c, that means that there is some elastic section in the cross-section. And if the thickness is just equal to c, which is the height, that means that the cross-section is fully elastic. Second, we want to solve for the moment that makes the whole cross-section elastic. To do this, we need to assume that the thickness of the cross-section is the same as the height of the cross-section. Lastly, we want to solve for the moment that makes the whole cross-section plastic. This means assuming that the thickness of the elastic section is 0. In order to solve for this, we need to know some relationships. We might want to know the relationship between the yield strength and the maximum bending moment that makes the whole cross-section elastic. When plugging in the moment of inertia for a rectangular cross-section, this equation can simplify to this. We will also want to know how to find the moment corresponding to the thickness
of the elastic section. Now that we know everything that is given and all the equations that we will need, we can start solving for our values. When solving for the thickness of the elastic section corresponding to the external bending moment, we will want to use this equation. We want to rearrange this equation to isolate for the thickness, which is done here. This step all the way through this step. Once we isolate for the thickness, we can sub in our given values to solve for the thickness. Remember to take into account units as they are not consistent in this question. In this example, we will be converting all the units to standard units. This is shown over here. This will result in a value of 0.0224 meters, which is the equivalent of 22.4 millimeters. Since this value represents half the thickness of the elastic section, the thickness of the elastic section is double this, which is 44.8 millimeters. This means that there is an elastic section when this moment is applied, and the thickness of that section is 44.8 millimeters. This will result in a cross-section looking somewhat like this. In this cross-section, the black area represents the plastic section and the blue area represents the elastic section. Next, we want to use the same equation to solve for the maximum moment that will result in a fully elastic cross-section. Along the way, we will also derive an expression that represents the maximum moment that results in a fully elastic cross-section for a rectangular cross-section. That expression was outlined above, over here. We know that in order to have a fully elastic cross-section, the thickness of the cross-section needs to be equal to the height. This means that we will set yy equal to c and solve for the resulting moment. Doing this will result in the expression that we outlined above, which is right here. Now we can sub in our values, keeping in mind the units, to solve for the moment. This will result in a moment of 25 kilonewton meters. This means that when this moment is applied, the cross-section will look something like this, in which it is fully elastic. Finally, we want to solve for the moment that will result in a fully plastic cross-section. Doing this would mean that thickness of the elastic section would be 0. Plugging in 0 for the thickness of the elastic section will result in this expression, which simplifies to this expression. Subbing in our values, keeping in mind the units, will result in a moment of 37.5 kilonewton meters. This means if this moment is applied, the whole cross-section will be plastic. This will result in a cross-section that will look something like this. This is it for the example problem. Thank you.